Hello. In this video, we are going to cover hypothesis testing, or at least a continuation of hypothesis testing, because in the last video, we introduced hypothesis tests, but we didn't really get all the way through them. We just went through and defined all the terms, defined the notation, and basically got things started. And then in this video, we conclude hypothesis testing by actually doing some hypothesis tests. All right, so to start, one thing that we did not cover in the last video is that hypothesis tests follow a data cycle type structure. So we covered the data cycle all the way back at the very beginning of this course in one of our earliest videos. But just to recap, here it is. So step one, in the first step of a data cycle, you go through and you ask questions. So what we're going to do is we're going to do all of the null hypothesis and alternative hypothesis stuff. We're going to figure out what our claim is. All of that's going to happen in step one. So we've already gone through and we've done that. So we're going to consider this step to have been accomplished in the last video, where we went through and found null and alternative hypotheses. So step two is the consider data phase for the data cycle. In that phase, we're going to be going through and either collecting data by actually doing experiments, like dice rolling or whatnot, or we're going to be finding data. And if we go through, and in either case, we're going to go through and we're going to check distribution requirements. So as part of going through and doing a hypothesis test, one of the things that we need to have is we need to have a normal distribution for the outcome. And that's dependent upon the sample data that we're going to use. It has to meet the central limit theorem requirements. Okay, so we need to go through and test that. So in the consider data phase, first step, we collect the data. I guess let's say we collect a sample. Okay, we collect a data sample. There we go. We collect a data sample and then check that our sample meets the central limit theorem requirements. All right, this is bugging me. That looks like a K. All right, I'm going to star this because it's something that we did not do in the last video, and we're going to go through and do that in this video, just for completeness sake. All right, so step three. In the step three of the data cycle, we analyze the data. In the data analysis step, we're going to go through and we're going to identify the significance level. We're going to calculate the test statistic, and we're going to go through and we're going to find the p-value. And so that stuff is stuff that we have not done in altogether. So we're gonna do that. We're gonna talk about more of that. We're gonna talk more about that in a second. All right, so in the analyze data phase, keep wanting to call them phases. I guess they're steps. In the analyze data step, we state the significance level. Calculate the test statistic. And find the p-value. So these are all things we talked about in the last video. And then finally, step 4, and I'm going to star that because I don't think we've done that in its entirety. And then step 4, in the interpret data step, we choose to either reject or not reject the null hypothesis. And I'm going to star that too, because I don't think we've done that. So we're going to talk more about all these starred things in the next few minutes. So that's going to be what we go over. All right, so that's a hypothesis test, beginning to end. It's a 4-step process. So you want to do step 1, find consider what the claim or the hypothesis is, find the null and alternative hypothesis. Then step 2, we're going to go through and we're going to collect sample data. And by collect, quote unquote, that could mean look it up, or it could be go through and do some type of an experiment, or collect the data ourselves. So, and then that we need to check that the sample meets the central limit theorem requirements. Step 3, once we have done that, we're going to go through and we're going to put all the data stuff together. So we're going to have like the number stuff, so significance level. We're going to calculate the test statistic for our sample, and then we're going to go through and find the p-value. Okay, and we're going to talk more about this in just a second. I'm just highlighting the process. And then step 4, at the end, you reject or you choose not to reject the null hypothesis. All right, so let's go through, and I want to talk about these starred things because those are things that we really haven't done yet. So step 2, we're going to need to go through and check central limit theorem requirements. All right, so how do we do that? In the same way that we did when we went over the central limit theorem. So why do we need to do this? So when we go through and calculate the p-values, so got to go back and go back and check the last video to recall what the p-value is. The p-value is the probability of getting an outcome that is as extreme or more extreme than the test statistic. And that is found by going through and finding, so when you're taking test statistics and turning them into probabilities, you're finding area under the curve. And if you're finding area under the curve, you need to have a normal distribution. So all of this is just a long way of saying that we have to have a normal distribution to go through and perform the hypothesis test. And how do we get a normal distribution? When we just have a population and a sample from that population, which is the information that you have when you do a hypothesis test, the central limit theorem. So the central limit theorem is what enables us to go through and take, this situation where we've got, a population, which could be dice rolls, or it could be voters, and then take a sample from, dice rolls, like you have like an infinite number of dice rolls as the population, and you'd go through and do a few dice rolls. That's the sample. You have all of the voters, in some voting situation versus a sample of them. It's a way to take that stuff and go through and say, how do we take that stuff and put some structure to it? And the way that you put structure to it is by going through and using the central limit theorem. So if any of that doesn't make sense, go back, watch central limit theorem video again. You can if you want. Anyway, but that's the idea, is that we're trying to go through and create structure. And then once we have some structure, we can then actually do stuff with it. We can go through and do probabilities and things. And so that's the reason that we're going through and doing the central limit theorem check, is to go through and get some structure that we can use for doing our test. And that structure in particular is to assume that samples are normally distributed relative to the population. Okay, so I'm not going to write all that down. I did in my notes. But what are the check steps? So, oops, this is step 2, then steps. This actually is steps, but I'll indent here. So it's the central limit theorem check steps, just to kind of separate it from the steps for the hypothesis test. So number 1, you've got to check that the sample is collected randomly. Number 2, you've got to check that the sample is of sufficient size. And the way that we do that is by doing the sample times the probability from the population is greater than or equal to 10, and then the sample times 1 minus the probability of the proportion is greater than or equal to 10. And then 3, you gotta check that the population is large. Relative to the sample. So all this is covered in the central limit theorems stuff. So, but if you do n, which is the population size, is greater than or equal to 10 times little n, which is the sample size. All right. So that. Oh, and then there's actually a 4th step I forgot. This is not in the central limit theorem. Well, central limit theorem section I think includes it in step 1, but they want you to go through and check that outcomes are independent. Let's do it this way, actually. Independent outcomes. So what does that mean? It means like if you were going through and checking like some kind of a dice roll claim or the coin spinning from the last video, that if you go through and you spin the coin, it somehow does not affect the results of the next spin. All right, so you need to have independent outcomes. Or when it comes to collecting sample data, like it's part of, as part of doing a survey, that the survey results are, the individuals in the survey results are independent. So there's no, the survey is unbiased. Basically, it's the same way of saying that the survey has to be random. But if it's random, but it's random in a biased way, then that's still going to cause a problem for going through and doing your hypothesis test. So you need to have independence. Like you can't go through and be surveying voters and then only survey voters from like a particular magazine, which happens to have a partisan lean of some kind. Like that would not be independent. Then suddenly all your readers have something in common. Or sorry, all your survey people have something in common. They're not independent. All right. So anyway, so that's step 2. We got to go through and check the central limit theorem requirements. So there is an example. I do have an example here of how to do this, even though we've done it before. So this example is just following up on the last section where we did home ownership. So in that example, we went through and we looked at, I gotta go back and look at it because I forgot what it is. Okay, I looked it up. I forgot to write it down. So in that example, we had H naught was that the population was 69%, 69% of homeowners. 69% of households were homeowners. And so that was our null hypothesis. And then the alternative hypothesis was that homeownership rates have declined. And so we're looking at less than 0.69. Then we went through and collected some random data. We looked at a sample. We did some sample data, and from the sample data, we got 63.5% were homeowners, and the size of the sample was 2,000. 2,000 people were interviewed or surveyed. All right, and so we just go through and do our central limit theorem check. One, is it random? The problem says it is. So you just kind of have to just trust the surveyor that the survey is telling the person who did the survey is telling the truth. And then for the sample size, you do 2,000. Now you do it times the population. So don't use the sample size. Sorry, don't use the sample percentage or proportion. All right. Did I write this down? Yes, I did. All right. So this is 1380. And then it has to be bigger than 10. 1380, much bigger than 10. And then you do times 1 minus this. And you get 620. And that also has to be bigger than 10. So that's the sample size requirement. And then step 3, this is more just a thing that you think about. If you went through and took 10 times 2,000, is the population bigger than that? Well, we're talking about homeowners. I'm sorry, we're talking about households in the United States. All households in the United States are clearly bigger. Is clearly bigger than 10 times 2,000, right? 10 times 2,000 is 20,000. There's way more households than 20,000. All right, and then step 4, independence. This is another one. You just have to trust that the person who did the survey says they're independent. All right, and that's the check. That's it. All right, so that's step 2. So when you get to step 2, you're going to go through and you're going to check the central limit theorem requirements, and you're going to collect the data if you don't already have it. In the problems that we're doing, the data will be given. But like if you were using a hypothesis test in the real world, like in some other class, then you'd probably go through and do some research. You'd find some data, and then you'd want to check the data meets the requirements. And so you'd also there'd be an extra step there where you'd have to go through and find the data. All right, so step 3, finding the p-value. Oh, well, there's more than just there's a bunch of parts in step 3. I mentioned going through and finding, stating the significance level and finding the test statistic, but we did both of those in the last video. I don't think we found the p-value in the last video, or at least I went through and I wrote out how to do it in this video. So if we did, we're going to do it again. All right, so to find the p-value, we need to find probability hold on one second. Yeah, couldn't read my notes there. Probability of an outcome that corresponds to the test statistic or anything more extreme. So this is a little bit complicated because of the fact that there are a few different types of tests. All right, so what I'm going to do is I'm going to break it down into cases. So case one, if the alternative hypothesis has not equal to, you're going to need to do a two-tailed test. So what does that mean? Where's that coming from? All right, so if your alternative hypothesis is that the proportion is not the same as, it's not P naught, right? So it's whatever P, so P naught comes from the null hypothesis. If your statement is that the proportion is not from the null hypothesis, then there's two ways that can be true. It can be true by having an extreme value that's less than P naught, and it can be true if there's an extreme value that is larger than P naught, right? So let's say that your null hypothesis is that is 50%, that 50% of something or 0.5 proportion of something is the case. So whether you could use that for voters, you could do that for coin flips, whatever. So the null hypothesis is that 50% of something is true. All right, well, there's two ways that can be wrong. That can be wrong with if 20% is true or 15% or 10%, like something that's way less than 50%, or it can be true if 80% or 85 or 90% is the case, right? So there's two ways, both to the left and to the, and to the less than, which I think of as the left because I'm thinking of number line, or to the right, or greater than, where this can be wrong. And so because of that, there's because of the two possibilities, that's why you have a two tail. So that's the two tails comes from those two cases. All right, and so we're gonna have to do something a little bit different when we find the p-value, which is the probability of an outcome that corresponds to the test statistic. We're gonna have to do something a little bit different because of that. And then two, we have, if the alternative hypothesis is P is less than P naught, then this is a one-tailed test to the left. And by left, again, thinking just in terms of a number line, it means that it's less than goes with to the left. And three, if we have P greater than P naught, then that's a one-tailed test. To the right. All right, so those are the three different cases. Let's take a look. I've got a visual for that. All right, and so here you can see the three different cases. So again, what we're doing, so in each of these cases, this test statistic is 1.56. All right, so if you've got a 1.56 test statistic, so that's the result that you got. Well, I'll talk more about that in a minute. All right, so what you want to do is you want to find the probability that goes along with that test statistic. And the way that you do it is you find area under the curve. All right, the area under the curve is how you translate from a test statistic or a z-score to a probability. So this is from the normal distribution section, so you can go back if you're a little confused and watch that, but that's how you go from, so test statistic is a z-score, which I covered in the last video, and then there's a lot of different pieces. It's very complicated, but you got to put them all together. So the test statistic is a z-score, and the way that you go from z-scores to probabilities is by finding the area under the curve. And what you do with a two-tailed, so you see two tails visually, is you go through and you find the area under the curve that's to the left of the test statistic, the negative version of the test statistic, and to the right of the positive version of the test statistic. So you find the area that's under both of these two sides, and that is going to be your p-score, right? That's your probability value that went along with the test statistic for two tails. All right. If you have a one tail that's to the left, then you go through and you take your test statistic, and you want to find the area under the curve that is to the left of it. So in this case, it's 1.56. So it went from, from negative infinity over here up to 1.56. Frequently, when you're doing a case with p less than, when you're doing less than or a left tail, it's going to be on this side. So it'd be like more likely you'd have negative 1.56. So I'm just giving you a heads up there. But you want to go through and find the area under the curve up to the test statistic. All right, and I'll show you how to do that. We did it in the normal distribution section. You're going to use StatCrunch for that, or some other software. You're going to use software for that. All right, and then finally we have the right tail, and you can see the right, it's shaded to the right because that's the area that's under the curve to the right of the test statistic / z-score. Okay, and so again, the way that we're doing here is we're just translating from test statistic to area under the curve, which gives us the probability. Okay, so that's how you go through, that's each of the 3 different cases, and that's visually what they look like, and with an explanation for why. All right, so let's go back and do an example. How do we find a test statistic? Sorry, how do we find a p-value given a test statistic? So in this case, what we're going to do is we're going to look at one of the problems again from the last section. So this one, we're looking at the coin spinning. So just writing that down. All right, and so what we had is we had our H naught was P equals 0.5. All right, and our alternative hypothesis was that the coin was biased. All right, that it did not give us a 50% result when we spun it. We went through and we collected some random data. So I'm going to do, this is different than what we did at the very beginning of the last video, but I quoted this at some point in the video where we said that we got 7 heads. So that would be out of 7 heads out of 20. So that's 0.35. And so we did 20 spins, we got 7 heads, so we got 35% of the spin results were heads. So that's our sample result with n equals 20. All right, so our test statistic. So I showed the math was calculated in the last section, but our test statistic. Now, what I'm going to do for this, just because it helps me to remember, /z-score. I'm always going to kind of throw in a z-score because that's what the test statistic is. That was negative 1.34. And if you remember, how did you get from here to here? It's in the last video. All right, so how do we go through and calculate the p-value? So to calculate the p-value, we got to go ahead and load StatCrunch, or you can use a software package of your choice. All right, so we've got it up here. And what we're doing here is we're using the normal distribution. That's the whole point of doing the central limit theorem stuff we talked about a few minutes ago. So we want to go through and we want to load the normal distribution calculator. All right, and so here, the normal distribution calculator, it's got everything here is in terms of z-scores. So we don't need to make any adjustments to the mean or the standard deviation. What we want to know is so we've got, so the thing, if you look at this, the default is that it only has 1 value. When we're doing a 2-tailed test, right, because we have not equal to, we want to go through and do between. All right, is there any way to switch this so that it does outside? No. Okay, well, that kind of stinks. But what we're going to have to do is we're going to have to do between, and then we'll subtract. So it's going to give us the middle, and then we're going to have to subtract from 1 to get the outside. So don't forget the area under the curve for a normal distribution, the total is 1. And so if you want just the stuff in the tails, and the only option is to get the stuff in the middle, you can still find the stuff in the tails by taking the total, which is 1, and subtracting what's in the middle, and that will give you the stuff that's outside. All right, so we have what, 1.34, so negative 1.34, and then positive 1.34. All right, and we got 0.81975. All right, so that's not weird. It doesn't look like it's symmetric visually. Okay, anyway, but I just was checking the numbers, make sure I entered them properly. All right, so that is the middle stuff. What we want is the stuff that's in the tails. So what you need to do is you need to do 1 minus that. So we don't want what's in the middle. We want the opposite, which is the outside stuff. So you got to do 1 minus that. All right, so you can break out a calculator for that. Just do 1 minus and then put 0.81975,466. And you get 0.1802. All right, so we got 0.1802. And that's the p-value. All right, and so that's how you find the p-value. Now, if we'd had a 1 tail, actually, I probably should have just done that without switching back. But if we'd had a 1 tail test, then you could go through and jump back to standard. All right, and you want to clear this out because we want to enter the value. And so you could do if it's, so I think our number was negative 1.34. So let's do negative 1.34. And this is a left tail. So this would be for a alternative hypothesis that's less than. So you'd have the p-value is 0.09. If we'd gone through and our result had been positive 1.34, then it would look like that. We'd have the p-value would be 0.9098. And then you can always switch it around to get it the other way. So if we'd had a right tail, or for an alternative hypothesis that was greater than, then you'd have greater than 1.34 as positive 0.09. Or if your test statistic had happened to be negative in that case, then it would be positive point. The probability, the p-value, which is a probability, but would be 0.909. Okay, so that's the basic for how to go through and calculate test statistics, depending upon whether it's not equal to for the alternative hypothesis, less than, or greater than. Those are the cases. Okay. So let's get to our last thing here. So you know what? Actually, I think I have. Whatever. We'll just do it. I was like, could it squeeze in down here at the bottom? Maybe. But let's just jump to a new page. All right. So example. Wait, no, not example. We just did example. All right, there we go. Step 4. Sorry. So reject or not to reject? To reject or not to reject? That is the question. All right, so the idea is behind a hypothesis test is we go through and we think of the default is that the null hypothesis is true. And so everything is couched in those terms. So when you go through and find the p-value, what you're doing is you're finding the probability that you would get the sample result, assuming that the null hypothesis were true. So you go through and you say, I'm going to assume the null hypothesis is true. So I'm going to assume that my coin is not biased, that it should give me, when I spin it, it should 50% of the time, it should give me a result. And then you go through and under those conditions, you figure out what is the probability that I would get the sample result that I did, 7 heads in 20 spins. Okay. And the same thing is true for examples that are not spins, right? So if you go through and you've got the home ownership case, right? So you go through and you say 69% of people are homeowners. You assume that that's true. And then you go through and you do a survey, and in your survey, you get 63.5% are homeowners. And so what you do is you say, all right, well, I'm going to assume the 69% is true. And then what is the probability that I would go through and collect a survey and get that 63.5% are homeowners? And so that's the idea. That's the structure of it. That's the basic, theory behind it. And so at the end, because the null hypothesis, because we're assuming that it's true, we're proposing or whatever, that we're defaulting that that's true. As a result, when we get to step 4, our result is focused on the null hypothesis. So even though the claim was the alternative hypothesis, you talk about the null hypothesis at the end, because we assumed it was true or proposed or whatever, used it as the default. We then go through and say, you know what, the evidence suggests that it wasn't true, or the evidence suggests that it was. All right, and so anyway, the point is that all the stuff I'm about to write is all in terms of the null hypothesis, and so that is why. All right, so how do you do that? So decide whether to reject the null hypothesis or not. We use the significance level. So in the last video, we introduced the idea of the significance level. So what is the significance level? The significance level is the probability oh geez. That we reject the null hypothesis when it was correct. So that's just the definition. The definition of the significance level is that we go through and we reject the null hypothesis when it is incorrect. All right. So because of that, the way that what we end up having here in step 4 is we have a competition between two probabilities. So if you're getting confused, you're like, wait, so I've got a p-value and that's a probability. I've got a significance level and that's a probability. Yes, exactly. You've got two different probabilities. And what we're going to do is we're going to pit them head to head. And the winner is going to decide whether we reject the null hypothesis or not. Okay. So you're going to compare the significance level to the p-value. If the p-value is less than the significance level, then it wins. The p-value wins, and then we reject the null hypothesis. If the p-value is greater than the significance level, then we fail to reject. So the significance level forms like a baseline for for where we decide to reject or not. So let's actually just think about this in terms of potential example, right? So suppose a p-level is 5%. So we talked about that in the last section as the default. Or sorry, that's not p-value, the significance level. Suppose the significance level is 5%. Okay, so what that is, what that serves as is it serves as a dividing line between where we're, how much evidence do we need to go through and decide that the null hypothesis was wrong or not. All right, so and so if our baseline is a 5% threshold, then the way to think about it is you go through and you collect all your data based upon the sample, and let's say the p-value ends up being 1%. So if you get 1%, that what that's saying is there's a 1% chance that you'd get the sample result that you did, assuming that the null hypothesis were true. So if the p-value is 1%, it's saying there's a 1% chance that you would get the sample result that you did. Okay, I could see how maybe that's not sticking. Let's say it this way, right? So let's say the p-value is 1% in the coin spin example, right? There's a 1% chance that you would spin the coin 20 times and get the result that you did. That's what that means. So if the p-value is 1%, it's saying there's a 1% chance that you'd spin the coin 20 times and get whatever outcome you got. All right. The significance level is going through, and it's just serving as a dividing line between when we have enough evidence to reject the null hypothesis and when we don't. So with 1%, 1% is less than 5%. And so we'd say, yep, we've got enough evidence here. We should reject the null hypothesis. The null hypothesis was wrong, right? Meanwhile, let's say you went through and you did coin spinning, and let's say that your result was a p-value of 10%. So that's saying there's a 10% chance that you'd get the outcome that you did, assuming that the null hypothesis was true. All right, so 10% is bigger than 5%. And so we'd say, 10%, there's not enough evidence here to go through and reject the null hypothesis. There's just not enough. 10%, that could happen. All right, that's a fairly high likelihood of an event happening. That happens 1 in 10 times. So you could have the coin spin, it might be biased, but if all your evidence is a 10% scenario, 10% happens often enough that that's just not enough evidence to go through and make a decision on. All right, and so that's what the significance level does, is it serves as this baseline for when do we reject and when do we not reject. Okay, that's the idea. All right, so that's what we're going to do at this last step, is we're going to go through and we're going to compare the p-value that we got, which again is the probability of getting the outcome that we did from the sample, assuming the null hypothesis is true. We compare it to the significance level. If it's less than the significance level, then we say that's enough evidence. So a 1% probability event, that's a lot of evidence. That only happens 1 in 100 times. And so it suggests that if something only happens 1 in 100 times, if the null hypothesis were true, then that suggests the null hypothesis wasn't true. Like 1 in 100 times is a very unlikely event to happen. Anyway, that's the idea. So that concludes all of the extra stuff. What's left here is we have examples. A couple examples where we just go through the process beginning to end. All right, so we're just going to do a hypothesis test in its entirety all the way through. All right, so in the past, what the past is, I don't know, but the idea is in the past, 39% of 45 to 59-year-old men were active. This is researchers, but it could be medical professionals. That varies. People are concerned the percentage someone's just concerned the percentage declined. So what they did is they went through and did a survey. They took a random sample of 1,927 men. Of that sample, 680 said they were active. Physically active, I think is the implied. They were physically active. All right, so let's go through the steps. Step one, hypotheses. All right, so we've got the null hypothesis and the alternative hypothesis. So the null hypothesis, so we got to go back. They say that the baseline for the population is that 39% of 45 to 59-year-old men were active. So that's what we use. So we're going to say the proportion is 0.39. And then their researchers are concerned the percentage has declined. So what we're doing is we're testing the hypothesis that less men are active. So we want to use less than. Step two, central limit theorem, check. All right, and so what we want to do is we want to go through. Our survey is, oh, sorry. The first step is it random? I almost skipped a step there. Is it random? I took a random sample, so yes, supposedly. Step two, sample size. And so what we want to do is just want to do 1927 times 0.39 and 1927 times 1 minus 0.39. And you want to check those are both greater than or equal to 10. And I can tell just by looking at them that they are. Step three, population size. All men, I guess not all men, but 45 to 59-year-old. It's definitely greater than or equal to 10 times 1927. They're definitely more than 45 to 59-year-old men than 19,270. And then for independence, we assume that's true. That's not spelled correctly though. Independent. Yep. All right, that's step two. Step three. What is the significance level? I didn't state it, but it is in the problem that the significance level is 5%. That is the default. What is the test statistic? So now we're going through and we're finding, this is to find the z-score for the sample. All right, so to do that, you first need to go ahead and convert the sample to a percentage or a proportion so that we can compare it with our 39% or 0.39. All right, to do that, you need to take 680 divided by 1927. You can just do that off to the side. Let's do so 680, 1927. And I think I did this for us. It is about 0.3529. All right. Once you've done that, what is the test statistic? The test statistic is p hat minus p naught over the standard deviation. All right, and so that is going to be, so this is p hat right here. That's the sample proportion. So that's 0.3529 minus the actual, which is, what was it, 39? Yep. Over minus 0.39. And then the standard deviation is calculated by taking the square root. 0.39 times 1 minus 0.39 over 1927. Right? Is that correct? 1927. Yep. All right. So the formula wise, you take this is P naught, which is the percentage. This is the proportion for the population times 1 minus P naught over N. All right. So it does not use P hat. You want to make sure to use P naught. All right, and so you go through and you can punch all that into your calculator and you should get approximately negative 3.34. All right, so that's the test statistic and then the p-value. So this is the probability. This is the probability that if we went through, if this is the probability that if this is true, what's the probability that 680 men would say they were active out of 1927? So you're finding the probability that your sample would be true, assuming the population value from the null hypothesis. All right, and so to do that, we need to get our StatCrunch out here. All right, and so what we're doing is we want less than, so you can change this to less than. All right, except ours is not negative 1.34, it's negative 3.34. The probability of that is, or the area under the curve, which is the probability of that happening, or something more extreme, is 0.00041889. P-value 0.0004 something. I don't remember. It doesn't matter. All right. Step 4. So our significance level was 5%. So 5% as a decimal is 0.05. All right. So that's our baseline. That's what we're using as how much evidence do we need to say that the null hypothesis was wrong? All right. So how rare an event does our test statistic need to be relative to our population? How rare does it need to be for us to decide that the null hypothesis is wrong? All right. It needs to be an event that happens less than 5% of the time. What did we get? As a percentage, this is equal to 0.04%. Move the decimal point 2 places. 0.04%, that's way less than 5%. So again, the way to think about this is it's saying if 39% of 45 to 59-year-old men are active, then there is a 0.04% chance that 680 out of 1927 would say they are. 0.04%. If this is true, there's a 0.04% chance that 680 out of 1927 would say that they are active. That is 0.04%. That's all but impossible. There's no way that 680 men would say they're active out of 1927. That's like well, I mean, you can go through and figure out what the 1 in a whatever is, but it's at 0.04% is really, really tiny. And so what does that tell you? If this is true, ends up getting you a 0.04% probability event, then it suggests that this was not true, that P is not 0.39. It suggests that the alternative hypothesis is correct. All right, so step 4, since the p-value is less than the significance level, we reject the null hypothesis. All right, so the null hypothesis, we reject it, and thus that suggests that the evidence suggests that the alternative hypothesis is correct, and that the men are less active. All right, I've got another example. You can see 2 of them. In a recent Florida election, 47% of registered voters voted. All right. A researcher wanted to check whether political scientists vote on a higher percentage basis. So they did a random sample of 47 out of 54 political scientists say they voted. Test the hypothesis with a 5% significance level. All right. Step 1. All right, so the claim, want to check whether political scientists vote in higher on a percentage basis. All right, so that suggests the alternative hypothesis is that the percentage is greater than 0.47 for political scientists. And the null hypothesis is going to be, nope, it's not greater. It's the same. Step 2, we've got our central limit theorem. Checks. 1, is it random? It says it is a random sample. Check. 2, sample size. Sample size, we take the size of the sample, 54, multiply it by the population percentage, 0.47. I did check this one. It is, you get 25, definitely greater than 10. 54 times 1 minus 0.47, 29. That's also greater than 10. All right, and step 3, population size. All right, so do we think that all registered voters in the state of Florida is greater than 54 times 10? Yes, right? And then step 4, which I ran out of space, is independent. All right. Step 3. Significance level is 5%. Test statistic. Yeah. Slash z-score. So we need to go through and do 47 divided by 54 to get the purport to turn our sample data here. The information they gave us, we need to turn that into a proportion or a percentage to compare it with the percentage that we were given for the population. And it is 47 over 54. It's about 0.74. All right, and then from there we can do 0.74 minus 0.4, was it 49 or 47? 47. And I can never remember these little details. Divided by the square root, we've got 0.47 times 1 minus 0.47 over 54. You do the number crunching with a calculator, and you're going to get 3.975. At least that's what I got, 3.975. All right, so what is that? That's saying that that's the z-score for receiving a 74% result when you expected a 47% result. So you'd anticipate that you're going to get a pretty high number. 74% is pretty far from 47%. All right, and then to get the p-value, we break out the stack crunch. Oh, we got 3.975. That's what we got to remember, 3.975. All right, so we want to do 3.975. And this time we're finding the alternative hypothesis is greater. And so the probability of greater than 3 getting a result that's the probability of getting a result that's greater than the 3.975 z-score is 0.000035. 0.000035. 0.000035. I don't remember. It's hard making videos. I'm distracted. Yeah, there's 4 zeros. Okay. It's a little distracting when you're recording and trying to remember things at the same time. All right. The p-value is that. All right, and then step 4. So again, I've said it a bunch of times, but I want to make sure that you're getting it because this is an important part of it. What that's saying is that the probability that you'd go through and talk to 54 political scientists, and 47 of them would say that they voted when the actual percentage of them that voted was 47% of 54. That's a 3.975 standard deviation event. The probability is microscopic. If you expected 47% of the political scientists to vote and 74% did, that's going to be a really unlikely thing to happen. Like you picked, assuming you picked randomly, you got really bad luck. All right. So anyway, the p-value is less than the significance level. Thus, there is sufficient as evidence to reject the null hypothesis. Okay, so I did the examples that are from the text, and there doesn't have to be, we didn't happen to do one where the p-value was greater than 5%. I just want to like briefly mention what would happen. All right, so let's just as an alternative history or alternative situation here. Suppose we'd gone through and done this and we'd gotten 0.35, not 0.000035, 0.35. Now 0.35 is the same thing. I don't know why I was about to put approximately. It's exactly the same thing as 35%. So if we'd gone through and interviewed our professors, our political science professors, and we'd gotten, let's say 0.5 or something like that, instead of 0.74, then we would have gotten probably something in the neighborhood of a 35%. What that's saying is that there's a 35% chance that you'd go out and you'd randomly select professors, and 50% of them would say that they voted when the actual result was 47%. That's what that's saying. Okay, is it's get the p-value, it's giving you the probability of the event. So if there's a 35% chance of an event happening, that's pretty high. That happens 1 in 3 times. And so because of that, we'd say there's not enough evidence to go through and reject the null hypothesis. So in this case, the p-value is, when the p-value is greater than the significance level, there is insufficient evidence. So we fail to reject. There's not sufficient evidence to reject the null hypothesis. So that's the way that you'd think about it. And so in terms of the, like a homework question or something like that, what you can do is we fail to reject the null hypothesis. This is the fail to reject case. Okay. And so that's just an alternate. If we'd done an example like that, that's what it would have looked like. And that's what the language would have looked like. All right. So that's it for this video. Thank you for watching. See you next time.